Let us briefly look at equation-based simulation for the buck boost and the buck boost converter. So I have within the work folder three folders: buck, boost and the buck boost. So let me open the buck. There are, as usual, two important files, model.m and sim.m. So let me open the model.m and look at the equations here which represent the buck converter. Let me bring your focus to these two lines here. They are basically representing the dynamic equations of the buck converter. See, IL dot, if you look at the inductor here, the voltage across the inductor is what is represented in this equation, which is V in into U, this node voltage at P. U is basically either 1 or 0 depending upon whether it is connected to T1 or T2. During DTS period, U is 1. During 1 minus DTS period, U is 0. So the U is actually coming as the output of a PWM block where you give the switching frequency, duty cycle and T, and then accordingly this U comes as output of the PWM block. And VC is the voltage across the output, which is the capacitance. So that minus VC by L will be IL dot. Likewise, the voltage across the capacitance is the other state. C dVc by dt is IL minus VC by R naught. So these two are the dynamic equations, and we pass as the output parameter X dot, which is IL dot and VC dot, and the X, which is coming in as an input to this function, is actually representing the two state variables IL and VC as shown here. So I have set these parameters V in as 12, similar like what we simulated in ngSpice, similar parameters, and this is ready for simulation in Octave environment. So now let me go into Octave, go into the buck folder and execute the sim file. So the simulation is performed. So what we are viewing is the output voltage in blue here. The red is basically the pulse width modulated waveform which is initiating the switches, and there is a black waveform which is the inductor current. We can zoom in. Let me take the Z plus or the zooming and zoom into a portion near steady state here, and you could probably see the inductor current and the duty cycle waveforms which are given to the switches. So like this, you will be able to see the various waveforms and simulate and validate the buck converter circuit. In a similar way, one can also do the equation based simulation for the boost converter circuit. Let me open the model file relating to the boost converter circuit, and we have discussed the boost converter, and you will be able to appreciate the equations here. See, IL dot is V in minus VC multiplied by 1 minus U. So when this switch is on, U is 1. So at that time, this node potential is 0. So that's what 1 minus 1, 0. And when the switch is connected to T2, through T2, then U is 0 and VC is applied at this node of the inductor, and thereby causing the inductor current to discharge into the output capacitance. Likewise, the other dynamic equation here, C dVc by dt is 1 minus U into IL minus VC by R naught. So the current here is 1 minus u into IL only when this switch is off, that you see the current flow through here in this branch just before the capacitance. All else being same, similar methodology, you can execute the boost converter and check the waveforms, the various waveforms. Here again I am seeing the U, that is the switching signal for switching the switch, and the state values IL and VC. Let me go into the boost folder and let me execute the sim file. So executing the sim, you see the plots being displayed. The one in blue is the output voltage, and the one in red here are the pulse width modulated pulses, and the one in black here is the inductor current. And obviously you see here that at the end of 10 milliseconds steady state is not reached. You can continue the simulation further by using the resume command as we discussed earlier. So let me go into the sim file and put resume here and execute this simulation again. So it will resume from where you left off, and it will continue, the simulation will continue, and probably depending upon the time constants of the system, you will reach the steady state after a few more resume commands. So for example, I can still continue, resume is still 1, I will continue, so it will continue from that, and now almost it is reaching the steady state. In this way you can resume the simulation at any point in time by storing the last simulation step value of the previous simulation. So this is one of the advantage of the resume command, which we have seen earlier and which we can use here. Another primary converter, of course, is the buck boost converter. Let me open that also and see that the model here is this fashion. L dIL by dt is the current through this L, and during the time when the switch is connected to T1, you will see it is V in. So therefore V in into U. U is 1 when switch is connected to pole is connected to T1, and during the time when the pole is connected to T2, the output voltage is negative with the charge plus minus as shown here. We have discussed that. So therefore I am using minus Vc during the time 1 minus U. And the other dynamic equation is similar. 1 minus U IL flows in this branch to charge up this capacitance in the reverse direction during the time when the pole is connected to T2, and there is a continuous constant discharge from the capacitance minus Vc by R naught. So these are the two equations which define the buck boost converter, and you can simulate this in Octave. So in Octave we can go into the buck boost folder and run the simulation. So let me type sim and execute the simulation. So this is simulation for the buck boost folder, buck boost converter, and you see in green the PWM pulses. The one here in the red is the output average current V0 by RS, and this is the inductor current and the output voltage. Of course, the steady state has not yet been reached. Just like in the boost converter, you can use the resume command, make resume is equal to 1, and continue the simulation further till steady state is reached.